Hi everyone, I'm back with another video, but this is the first video of a series basically. In this video, I'd like to introduce you to a kit that one of my dear friends, who might be watching this, gave it to me. It's being used at Humber College, actually. I don't know which student years, but yes, it's being used there to teach hardware engineering, electrical engineering, and then I thought, okay, let me see how complicated or how simple this is. And my interest in it was pedagogical reasons, especially that it says, this is the box, it says ages 14 and up. Okay, and then this means that the concepts in a radio can be simply put such that a 14-year-old would understand them, hopefully some of it, or make at least understand enough to make it work, right? So this is the one. It's from WeMake, and then it's tools. They make tools for makers, and then it's a AM/FM superhet radio kit. It comes in this box. So this is basically the book or the booklet that explains everything. I looked at it a little bit, and then you know what? It goes through a lot of basics as well, like how to test a diode, or how to test, how to find out if your transistor is NPN or PNP. Very basic stuff that a person who's touching electrical components should be knowing, right? So this is the booklet. It has some theory in it, but it's not great in the theories. They're very, very brief. So that's when I'm coming in. So I thought, I'll go through the block diagram. This is the circuit, the whole radio. It's huge, right? This is the whole radio. I'll go through the block diagram of this, explaining how each submodule, or what are the submodules in a radio, and then we can dive into the different submodules and study the theory behind them, how we can, know enough that later, if you want to design our own power amplifier or audio amplifier, we would know some stuff. I love this, by the way, PCB, much more than a breadboard that usually electrical engineers are given. Well, electrical engineers are supposed to know how to make this, but I love it as the first step, because as the component goes on top of the board, right, you can see the circuit symbol underneath. So that's it sticks, it helps you with your visual memory, to learn that what are the different components, circuit symbols, and then it's easier than, I'm holding it to reverse, it's easier than working on a breadboard, because you have to constantly check the circuit and then bring it translated in your mind to the nodes of the breadboard. So if you're, again, that's probably why it's good for 14-year-olds as well. Anyway, so the booklet, this is the PCB that we'll be putting the components on, and then we have the AM part, FM part components, transistors, amplifiers, ICs, and then the speaker, and then also the battery, and then also the antennas to receive the AM and FM, waves, so that you can actually translate them to an audio that can be played on the speaker. Okay, so in this video, I'll start with the block diagram of this radio kit or radio circuit. Then hopefully as we move on, I'll introduce more and more and about the details of each submodule and see how we can do this. You can't believe how much you can learn from a radio. It has a lot of details, a lot of theory that, sometimes you're like, we don't even think about how it works, but it's the base of a lot of stuff. Microwave engineering, RF engineering, electrical engineering, it has a lot going on in it. Okay, I'm gonna stop talking now, and then next thing that you're gonna see is the block diagram of this. Okay, let's look at the block diagram of this FM AM radio. As you could guess, it has two parts. The lower part shows us the AM radio, and the upper part shows us the FM radio. Okay, and so we are going to look at the FM part and the AM part. Just because of simplicity, because it's simpler, I'm going to start with the AM part. This is our AM path, and this is our second path, the FM path. Okay, so first, AM path. What does AM mean? It means amplitude modulation, or amplitude modulated signal. Okay, and then that would tell you that the signal that we are interested in the audio signal, is actually sent through the amplitude of another signal. So our signal SAMT, let's call it, looks like a signal that is in the amplitude of it, and then the frequency is actually our carrier frequency. That's why this is called amplitude modulation, because we are putting our audio signal in the amplitude of the carrier signal. Okay, and then this is called the carrier frequency, or we can call it intermediate frequency, etc. You can find different names for it. Okay, but right at the beginning, we have to know what is this carrier frequency and how we can get our MT detected from the signal that we received, right? You might have seen the practice example where I talk about the FM and AM modulation, but we're going to quickly go over it again. So the first thing that happens is that we have a symbol here that shows this is our antenna. Okay, so an antenna, an RX antenna, let's say, will receive an AM signal. So whenever we say a signal, we have to know its amplitude, we have to know its frequency, right? The amplitude is going to depend on the signal, the audio signal that we are sending it, right? And then the frequency is kind of a known range, or the agreed range, and that's about 500 to 1700 kilohertz. Okay, and since our the signal is in the amplitude, we don't need a lot of bandwidth, and we can easily detect this with 10 kilohertz bandwidth. Okay, so the next thing we need to know is that, okay, what is the carrier frequency here? FC, or another term, IF, intermediate frequency. Here, early on, they used about 455 kilohertz, which was lower than the range of AM itself, but it was in a way that the filter that they were using, the LC filter that they were using, it was simple enough and cheap enough that they could actually detect, get the frequency, the IF signal out of our received signal easily. So that's why the 455 was used, and then it just stuck. So this is C, this is L. Okay, so this is one thing we need to know. So after the signal is received, the first thing we need to know is to get it mixed so that we can get rid of our carrier frequency. Okay, so what we will do is that we have a mixer and an oscillator. This AM oscillator, the job of the oscillator is to create the frequency of the carrier, or the intermediate frequency, to be mixed with our received signal. So here what we have is about a frequency that is about 455 kilohertz being generated. This oscillator is creating this frequency so that it can be mixed with our original one. Why? Because once you, let's say we are mixing SAT with exactly cosine 2 pi FCT. Okay, we are mixing it, we are multiplying it. Okay, when you multiply a signal that looks like this, 2 pi FCT with cosine 2 pi FCT, what happens? You would create two other signals. You would create a signal that has the frequency of 0, and then you would create another frequency that is double to FC, double the FC. So AC plus MT, and then cosine 4 pi FCT. Okay, and then by using the filtering, as I said, we only need 10 kilohertz, right? Because we only need this signal. Because the difference between 2 pi FC and DC value is a lot, and in the frequency spectrum right now we have a component that is right at the 0. I don't like the way I drew this, so let's call this 0. We have a frequency right here at the 0, and then we have a frequency at 2 FC, that is this one. Because the difference between these two is a lot, because 2 multiplied by 455 is about 9-10 kilohertz, and there's quite a difference between these two. Only by using a 10 kilohertz filter, we could just get these frequency, which is our amplitude, separated from the mixed signal. So that's why after the AM mixer, what comes out is our there should be a filtering after this as well, but like we can say that our base frequency comes out of here. Okay, base frequency, base signal comes out, it gets amplified multiple times, and then the AM detector actually finds what is our MT. The AM detector can be a simple filter at this point, right, to just get the DC component out, right? And then so here we are just detecting the amplitude, and then here we have an adaptive gain control, just to make sure that since our audio signal is in the amplitude, we are providing reliable feedback to the amplifier so that the amplitude can be detected properly. And then after that, we have a last level of the amplification after cleaning up the signal, just so before it is passed to the speaker. So this is our AM signal journey from the antenna to the speaker. Now we can go ahead and talk about the FM path. Okay, let's look at the FM path for a little bit. Okay, what the FM path does is it starts with the antenna as well, and then right after that we have a new component or a new block, which is FM RF amplifier. You're like, what is that? Why is it there, and why didn't we have it in the AM part? Okay, and notice that here we are talking about RF, not IF. These are all intermediate frequencies, but the only component that we have that works in the RF domain is that FM RF amplifier. Okay, So to explain that, we need to go through our RF path now. Let me see if I can copy this. Can I copy this here? Okay, I might not be able. But we have FM RF amplifier. So our journey of the FM signal starts with being received at the antenna as well. But just like AM, we need to know what is the frequency range, and what is the bandwidth, and what is the intermediate frequency. So FM is at a higher frequency. It's about 88 to 108 megahertz. And then we need about 200 kilohertz to detect it, to retrieve it. Just bear with me with that. We need a higher bandwidth. And then the intermediate frequency also is higher. It's about 10.7, almost double megahertz. Or sorry, not double, 20 times more than the AM signal. Since the frequency is higher, you see, the FM frequency is much higher than the AM. And this is something that radio frequency signals experience. As the frequency goes higher, the attenuation goes higher as well. So the signal that you would receive from the FM port or the FM antenna is weaker than the AM part, even if they just travel the same path, the same distance to get to your from the tower or whatever to your radio station, right? So they would experience different attenuations such that the FM signal becomes weaker. That's why we immediately after receiving the FM signal, we need to amplify it, because garbage in, garbage out. We amplify it before even passing it to the mixer, to the oscillator. So as we had here, FM signal comes in, we apply the RF amplifier, right? And then we pass it to the mixer, what we call the FM mixer. And this mixer, it has to get an oscillator frequency oscillator. This oscillation is going to be around 10.7 megahertz, because that's the intermediate frequency of our FM signal. And then once we do that, then we are working on the base signal. And then the rest of it is kind of the same, that we are going to amplify this signal. Here, we are just amplifying it till we pass it through the FM detector, where we are trying to find the frequency. And I'll explain it in a second. And we need to have an adaptive frequency control, because the frequency is the one that matters to us here, unlike AM, where the amplitude mattered to us. That's why we were adapting the gain. Here, the frequency matters to us, and then we are feeding that feedback frequency to the oscillator itself. So there are a couple of points to notice here. Let me start by, we talked about the AM signal. Now let me talk about the FM signal. The FM signal is such that the message that we are sending is going to get applied or change the frequency of our carrier signal. So we have amplitude is going to be normal, a constant, let's say, cosine 2 pi fct. And then the message is going to impact the frequency of our signal. So let me just write it as, like, let's say 2 pi t, and then multiplied by, or 2 pi. I'm trying to make it as pretty as possible. Fc plus a coefficient, then we say m tau d tau, and this is t. And then here comes t. So our message would impact the frequency. This is the frequency of this cosine signal frequency. So as you can see, now we have to kind of get this frequency out of the FM signal, and then out of the received signal, basically. That's why we need a different bandwidth. That's why we need to have an oscillation that is happening around at 10.7 megahertz almost, and this would be adjusted, right, constantly. And then after it is passed to the FM detector, which we will discuss when we are discussing the FM detector, then it passes through last stage of amplification and then a speaker. Okay, so I know there is a lot to digest, but I hope this would give you a brief, very brief explanation about FM and AM modulations and how they are used in the radio. And then again, in the next videos, we will mix the theory and the assembly and the circuits of each section, so we can talk about all the different 9 sections here. Next, what we are going to do is we will work on section 1 in the next video. I'll talk about the IC audio amplifier, the component we use for it, and the equivalent circuit, and then the gain that we can get from that that IC, basically. Okay, I hope you enjoyed it. If you did, please leave comments, so at least I know that this video matters to someone, and then it will give me motivation to continue the topic. If I see no traction on it, honestly, like, there is no point on me making these videos. So please like and subscribe. Thank you.